This video is a step-by-step solution for the example entitled Evaluating Heat Pump Performance. In this example, you will learn about using the limits imposed by the second law for a system undergoing a heat pump cycle to evaluate the minimum work input per day to provide heating to a building. You will also learn how to determine the minimum daily operational cost for this heat pump system. Let's look at the problem statement. A building requires 5 times 10 to the 5 BTU per day to maintain its temperature at 70 degrees Fahrenheit, when the outside temperature is 32 degrees Fahrenheit. If an electric heat pump is used to supply this energy, determine the minimum theoretical work input for 1 day of operation in BTU per day. Evaluating the electricity at 13 cents per kilowatt hour, determine the minimum theoretical cost to operate the heat pump in dollars per day. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. A building requires 5 10 to the 5th BTU per day to maintain its temperature at 70 degrees Fahrenheit when the outside temperature is 32 degrees Fahrenheit. The next thing to do is to summarize what we have to find. Part A, if an electric heat pump is used to supply this energy, determine the minimum theoretical work input for 1 day of operation in BTU per day. And in Part B, evaluating the electricity at 13 cents per kilowatt hour, determine the minimum theoretical cost to operate the heat pump in dollars per day. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement as a bulleted list. A heat pump maintains a building at a specified temperature, and the energy supplied to the building, the ambient temperature, and the unit cost of electricity are known. The next thing to do is to summarize what we have to find. This is essentially the same information we highlighted in green in our critical read of the problem statement, presented again as a bulleted list. The minimum theoretical work required by the heat pump, and the corresponding electricity cost. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few key pieces of information. The first thing to note is that there is no mass entering or leaving the system. This immediately suggests that a closed system approach is appropriate. Having recognized this important fact, let's select our system boundary. Remember that a closed system does not allow any mass in and out through the boundary. The only transfer allowed through the boundary are heat and work. Here it is selected to enclose the entire heat pump system as delineated on the schematic with the red dashed line. It clearly ties in the information provided to the information requested in terms of energy transfers. The heat source QC and its temperature TC. The house temperature TH to be maintained by the heat addition Q sub H. Note also that the heat addition was provided here on the time rate basis. Q dot H is equal to 5 10 to the 5th BTUs per day. And finally, the work input to the heat pump cycle, W cycle. The next step is to develop an engineering model. In other words, listing a set of simplifying assumptions which will allow us to perform the analysis of the problem. The system shown on the previous schematic executes a heat pump cycle. The building and the outside air play the role of the hot and cold reservoir. The value of the electricity is 13 cents per kilowatt hour. And the energy transfers are positive in the directions of the arrows on the schematic. Having completed all the required initial steps, let's start to develop the analysis. Using the equation for the coefficient of performance for a heat pump cycle, gamma, the work for any heat pump cycle can be expressed as follows. W cycle is equal to Q sub H divided by gamma. The coefficient of performance gamma of an actual heat pump cycle is less than or equal to the coefficient of performance gamma max of a reversible heat pump cycles when operating between the same two thermal reservoirs. Gamma is less or equal to gamma max. Therefore, for a given value of QH, the work required can be expressed by the following inequality. W cycle is greater or equal to Q sub H divided by gamma. Using the expression for the maximum coefficient of performance for reversible heat pump cycle allows us to evaluate gamma max in terms of the given temperatures. We obtain the following expression. W cycle is greater or equal to 1 minus T sub C divided by T sub H times Q sub H. Using the expression for gamma max is equal to T sub H divided by T sub H minus T sub C, and substituting the temperature value gives us gamma max is equal to 13.95. By using this value we just calculated for gamma max and substituting into the expression for the work of the heat pump yields the following inequality. W cycle is greater or equal to 3.58 10 to the fourth BTUs per day. Therefore, the minimum theoretical work input for the heat pump system is 3.58 10 to the fourth BTU per day. This is the first answer we were seeking. Keep in mind that this minimum theoretical work value was arrived at by considering the maximum theoretical coefficient of performance for the heat pump based on the specified temperatures. For part B, we use the result we just obtained for the minimum work input, together with the given cost data for the electricity. Note that we also performed the required unit conversions to go from BTU per day to the price of electricity per kilowatt hour. The minimum theoretical cost per day is $1.36. This is the second answer we were seeking. It is important to realize that this apparently mixed unit system used in the specification of the problem, while sometimes very cumbersome, is very typical of everyday engineering practice, where heating and cooling loads for building are often specified in BTU per minute or BTU per hour, while electricity consumption is measured in kilowatt hour. Therefore, being proficient in unit conversion in the energy field is an essential skill. To conclude this example, I would like to make a few remarks. As mentioned earlier, the temperatures T sub C and T sub H used in evaluating gamma max must be expressed as absolute temperature, namely in Kelvin or degree Rankine as appropriate. Because of the many irreversibilities, an actual heat pump an actual heat pump system will require more work than the theoretical minimum to provide the same heating effect. Therefore, the actual daily cost will be substantially greater than the minimum theoretical cost we just computed. However, if properly designed and sized, heat pump systems are often financially viable alternatives for heating buildings, depending on climate and heating requirements. This simple example gives us a brief glimpse into the field of thermoeconomics, where thermodynamics provide a basis for evaluating the economic viability of systems. Quick quiz. Part A. If a heat pump whose coefficient of performance is 3.0 provides the required heating, determine the operating cost in dollars per day. And in Part B, repeat the cost analysis if the heating is provided by electric resistance baseboard heating. You may want to pause the video at this point to answer those questions. The answer for Part A is $6.35 per day and $19.04 per day for Part B. Hopefully, those are the answers you have obtained. If not, carefully review this video and the various derivations, and check your calculations. Those answers to the quiz questions illustrate vividly the fact that heat pump cycles, with their coefficient of performance greater than 1, typically around 3 or 4 for practical systems, potentially represent significant savings compared to the direct use of electricity for providing resistance heating. In summary, in this example, we have learned about using the limits imposed by the second law for a system undergoing a heat pump cycle to evaluate the minimum work input per day to provide heating to a building. You have also learned how to determine the minimum daily operational cost for the heat pump system. This concludes the step-by-step solution of the example entitled Evaluating Heat Pump Performance.